A buoy in the form of a hollow spherical shell of external radius 1 meter and internal radius 0.8 meters floats in water with 61% of its volume immersed. Find the density of the material of the shell. Okay, let's look at the forces on it. We have its weight, mg, and there's a buoyancy force, equal and opposite. Let's suppose that the density of the shell is rho. We will get m in terms of the density. We can find the volume. We want the volume of the outer sphere minus the volume of the inner sphere. That'll give us the volume of the shell. Okay, the volume of a sphere is 4/3 pi r cubed. So we can factorize out the 4/3 pi. The outer shell is radius 1, inner shell radius 0.8, and we have to multiply by the density of the shell. Alright, we might as well get the weight of the shell. We just multiply by g. Now, we can apply the law of flotation, which says that the weight of the floating object equals the weight of the liquid displaced by the floating object. So, to get the weight of the liquid displaced, we need the volume of the liquid displaced. Well, that's equal to the volume of the immersed part of the sphere, which is actually 61% of the sphere. Okay, so the volume of the immersed sphere is 0.61 times 4/3 pi times 1 cubed. That's the volume of the entire sphere with radius 1. As the volume of the immersed part, that's equal to the volume of the liquid displaced. So here's the volume of the liquid displaced. We multiply by the density of the liquid. This is water. So water has a density of 1,000. Volume times density is the mass of the water displaced, and multiply by g to get the weight of the water displaced. Okay, multiply both sides by 3 over 1.952. 0.61 times 1,000 is 610. Alright, nearly forgot the 4/3. So we have to divide 610 by 1.952 and multiply by 4. So we get 1,250 kilograms per meter cubed. Notice that this figure here is greater than the density of water. It's greater than 1,000. So, you know, if this was not a hollow object, if it was a solid object made out of material with density 1,250, then it would sink, because it's more dense than the liquid. It's more dense than water. But because it is hollow space, the overall density ought to be less than the density of water. So I mean, the average density is going to be less than the density of the liquid that's supporting it. Okay, the average density is the mass of the buoy, which is just equal to the mass of the shell because zero mass inside, divided by the volume. If you do that calculation, you should get a value that's less than 1,000. So what counts for a floating object is the average density. So that's why boats made out of steel can float in water, even though steel has a density much greater than the density of water. A uniform rod of length 1.5 meters and weight W is freely hinged at a point P. The rod is free to move about a horizontal axis through the point P. The other end of the rod is immersed in water. The point P is 0.5 meters above the surface of the water. The rod is in equilibrium and is inclined at an angle of 60 degrees to the vertical. So we're going to get the relative density of the rod. So we have the density of the liquid. Liquid is water, so the density of the liquid, rho L, is 1,000. Okay, we've seen an example like this before. We get the buoyancy force on the immersed part, and we stated before that the magnitude of the buoyancy force is less than the magnitude of W, because the moments of these forces have to be the same about this point here. Let the length of the immersed part be x, so the distance from here to here is x divided by 2. So again, as in previous examples, we situate the buoyancy force at the center of mass of the immersed part. The rod is uniform, so the center of mass is the midpoint of the line that's immersed. Of course, W is situated at the midpoint of the rod. the center of mass of the rod. So the distance of W to P is half of 1.5 or 0.75. Okay, let's get B in terms of W. That's the usual procedure because we're going to take moments of these forces about P and equate the moments, so the W's will cancel, which will tell us something about what X is and hopefully the answer to the question, the density of the rod. So as before, B by the law of flotation is equal to the weight of the liquid displaced by this part of the rod. Well, actually we are applying Archimedes' principle here, not the law of flotation. By Archimedes' principle, B is equal to the weight of liquid displaced by the immersed part of the rod. And to get that weight of liquid, we need to get the volume of the liquid displaced by the immersed part of the rod. The volume of the liquid is equal to the volume of the immersed part of the rod, which is the length of the immersed part, which is x. Distance from here to here is x times the cross-sectional area of the rod, which we will call A. We'll get rid of that A soon. Times the density of the rod, which we are trying to find actually. I will call that rho r. So that's the mass. Well, actually, I'm mistaken here, not the density of the rod, but the density of water. Because by Archimedes' principle, the buoyancy is the weight of liquid displaced. So the volume of liquid displaced equals the volume of the immersed part of the rod, and the density of water is 1000. And we multiply by G to get the weight of water displaced. Now we need to eliminate A. That's the cross-sectional area of the rod. It's probably a very tiny cross-section for a thin rod. We get W in terms of A. So to get the weight of the rod, we multiply its length, 1.5, by the cross-sectional area to get the volume of the rod. Multiply that volume by the density of the rod to get the mass of the rod, and then multiply by G to get the weight of the rod. So we rearrange this to get A, and we sub this in up here, so we get B in terms of W. So A is W over 1.5, the density of the rod times G, multiplied by 1000 G. The G's cancel. Okay, so we have 1000 divided by 1.5, that's 666 2/3, and we've XW over rho r. Now we consider moments. So B has a clockwise moment about point P. Again, we consider moments about point P because any forces acting at point P have no moment about point P, because the line of action of these forces acting at point P passes through point P. The distance of point P to the line of action of these forces is 0, so they have no moment. So it's a very convenient point to take moments about. So we need to get the moment of B about this point. So we need to multiply the magnitude of B, which is just what we worked out, by the perpendicular distance of the point P to the line of action of vector B. This angle is 60 degrees, so this one here must be 60 degrees. We have a pair of Z angles. So this is the distance that we're looking for. To get that distance, we need to get this distance here and multiply this by the sine of 60 degrees, okay? So the hypotenuse of this right angle triangle must be multiplied by the sine of 60 to get the side opposite 60. Okay, so what is this distance? Well, it's the total length of the rod, which is 1.5, minus the distance from here to here, which is x over 2. So we multiply the hypotenuse of this triangle by the sine of 60 degrees. So that's the clockwise moment due to B, and it must equal the anti-clockwise moment due to W for equilibrium of this rod. So we have to take W and multiply the magnitude of W by the perpendicular distance of the line of action of vector W from point P. So to do that, we need this distance here, along the rod. So this distance here in blue is the distance from P to the midpoint of the rod actually, where W acts. That's half the length of the rod. Half of 1.5 is 0.75. So we have to multiply 0.75 by the sine of this angle to get the side opposite this angle in this blue right angle triangle. But what is this angle? Well, this angle is the same as this one here. It's 60 degrees, or we can say it's the same as this. So we have a pair of Z angles, or we have a pair of corresponding angles. Okay, so this angle is 60 degrees. So we multiply the magnitude of W by 0.75 sine 60. Multiply the hypotenuse 0.75 by the sine of 60 to get the side opposite this angle, 60 degrees, which is what we want. Now this looks like a horrible mess, but something that we can do here is work out x. I could have worked out x at the start, but it doesn't matter. The reason that we can work out x, that is the length of the immersed part, is because of we have all the information about this right angle triangle that I'm showing now. This right angle triangle in purple is fully specified actually. Alright, you see that we have an angle and we have a side. That means we can find a distance from here to here. That's the distance of the non-immersed part of the rod. Okay, and all we have to do then is just subtract this from 1.5. So we just need to find the hypotenuse here. So the cos of 60 is 0.5 over h, which means that h is 0.5 divided by the cos of 60. Okay, just interchange cos 60 and h. Cos of 60 is 0.5, 0.5 divided by 0.5 is 1. So now we have the length of the non-immersed part of the rod. This part here is 1 meter. So the part that's immersed is 1.5 minus 1, which is 0.5. So this part here is 0.5 meters. So that's x. So you can plug that x in here. See, I knew that something's not going right here because we have two unknowns. We have rho r and we have x. So we need to just back up if we miss something, and then, you know, realize that we can actually find x in this particular example. And it's clear that when we found x, the only thing missing will be rho r, because the sine 60 is just a number that goes, and of course the w's are gone. So we need to plug 0.5 in here for x, and we've 0.5 over 2, plug 0.25 in here. Okay, if you work this out, 416 and 2/3 over rho r equals 0.75. Just swap these around. So rho r is 416 and 2/3 divided by 0.75, which is 555.55 recurring. I've rounded to 0.56 here. So this is the density of the rod. Now we want the relative density of the rod. So that's the density of the rod compared to water. So we divide the density of the rod by 1,000, and if you do that, you'll get exactly 5/9 if you include all of the recurring 5s here. So the density of the rod is 5/9 the density of water. It's obviously less than the density of water. You know, it has to be less than the density of water for it to float in the water. In part 2, we want the reaction at the hinge in terms of W. Okay, let's just get B. We need the buoyancy force. We have X. We saw that X is 0.5. .5 times the density. Well, the density is 555.55 recurring, and we have to multiply by 1,000. Okay, we get B equals 0.6 W. Now, this rod is in equilibrium. We can see that both B and W have no horizontal components. These are not the only two forces acting on the rod, of course. If they were, the rod would not be in equilibrium. You can see that B has smaller magnitude than W. It's 0.6 of W. So there's obviously a force here in the vertical direction. It has to be in the vertical direction. It can't have a horizontal component, because if it did, the rod would move either left or right. So, and it must be upward, so that when we add it onto B, we get W. So if B is 0.6 W, then this force here must be 0.4 W. 0.6W plus 0.4W is 1W. The upward forces must equal the downward forces for equilibrium. So if we call this force R is upward and has magnitude 0.4W. A U-tube of cross-sectional area of 0.15 centimeters squared contains oil of relative density 0.8. That means that the density of the oil, written rho O here, is 0.8 times 1,000, which is 800. The surface of the oil is 12 centimeters, that is 0.12 meters, from the top of both branches in the U-tube. What volume of water can be poured into one of the branches before the oil overflows in the other branch? Okay, so let's suppose that water is poured in here, and we want to keep pouring in water until the oil overflows in this branch. Well, for the oil to overflow, this level must rise up 0.12 meters. And the level of the oil here will have to move down 0.12 meters. Okay, so what we do is we consider a point in the liquid just below the column of water. And we consider another point over here, which is at the same depth, 0.24 meters from the surface of the oil. So both of these points are in the oil. This point is just below the column of water, but it's in the oil. Now, since this point is just below the column of water, the force on this point is due to the column of water bearing down on it. So the pressure at this point is due to the column of water. Okay, so we know that pressure only depends on depth below the surface. So let's suppose that the column of water has height h. So we know that pressure is just density times g times h. We're talking about the density of this column of water now. Okay, remember where this formula came from. It came from considering a circle centered at the point in question, and we show that the downward force on the circle was equal to the weight of the column of liquid above it. So even though this point is actually in the oil, it's just below the column of water. So the same reasoning applied as when we derived this formula. But it's just to realize that we need to consider the density of water here, because the column is made out of water. Okay. Now the pressure at this point is the same. If we just consider the oil, a horizontal level in the oil. However, here we can actually calculate the pressure because we have the height of the column of oil above this point, and we have the density of the oil. So it's rho GH, where rho is 800. So it's 800 times G times H is 0.24 meters. Multiplying 800 by 0.24, we get 192. So we see that H is 192 divided by 1,000, which is 0.192. Now, if we just had one liquid in this U-tube, then the liquid would find its level. We'd have the same level on both sides, you know. If this was the level on the left-hand side, we'd have the same level on the right-hand side. But you see, we have liquids of different density in this U-tube, so the liquids don't level out at the same point. Since water is more dense than this particular oil, we need a shorter column of water to give the same pressure than a column of oil. See, a column of water 0.192 meters high supplies the same pressure to a point at the base of it as a column of height 0.24 meters of oil. We need a greater column of oil because it has less density than water. You know, the mass of both of these columns are the same. Anyway, we need to just get the volume of this column of water. Well, that's straightforward. We have the height. The cross-sectional area is 0.15 centimeters squared. So we just multiply the height by the cross-sectional area. However, we need to convert centimeters squared to meters squared. So we need to figure out what 1 centimeter squared is in meters squared. Well, we just draw a square of side 1 centimeter. So its area is 1 by 1 centimeter squared. But a centimeter is 0.01 meters. So the area in meters is 0.01 by 0.01, which is 0.0001 meters squared. So that's 1 centimeter squared. We multiply this by 0.15 to get the cross-sectional area of the tube in meters squared. Okay, so how many decimal places? We have 4 decimal places here and 2 here, so we'll have 6 altogether. 1, 2, 3, 4, 5. 1.5 here, I think. Okay, so here's the height multiplied by the cross-sectional area, and our volume, of course, is in meters cubed. A uniform solid cylinder floats upright with 1/3 of its axis immersed when placed in liquid A. When placed in liquid B, the uniform cylinder floats upright with 3/5 of its axis immersed. Okay, so here's a picture of the cylinder in liquid A. Let's apply the law of flotation to this object. It says that the weight of the object is equal to the weight of the liquid displaced by the object. So what's the weight of the liquid displaced? Well, it's the density of the liquid displaced times the volume of the liquid displaced. The volume of the liquid displaced is equal to the volume of the immersed part of the cylinder, which is 1/3 V, where V is the volume of the full cylinder. Okay, that's the mass of the liquid displaced. To get the weight, we multiply by G. We do the same here. The weight of the floating object is equal to the weight of the liquid displaced, which is the density of the liquid displaced, rho B, times the volume of the liquid displaced. That's equal to the volume of the immersed part of the cylinder. So 3/5 of the cylinder is immersed. Total volume is V, so the volume of the immersed part is 3/5 of V. Density times volume gives us the mass of liquid displaced, and we multiply that by G to get the weight of liquid displaced. Now, in the third situation, the two liquids are mixed together uniformly. So, you know, again we can apply the law of flotation. The weight of the object W, which doesn't change, of course, the W's are all the same, the object hasn't changed, is equal to the weight of liquid displaced. So in this case the density of this liquid I'm calling rho AB, and the volume of it displaced, well, that's what I'm calling VAB, this piece here. Now, what we will do next is get rho AB, the density of the mixture, in terms of the density of the constituent liquids, rho A and rho B. Here is one approach. Let's take equal volumes of liquids A and B. So let's take, say, 1 meter cubed of A and 1 meter cubed of B. It's a convenient number. Let's let 1 meter cubed of liquid A have mass MA. Then the density of it is mass over volume. Well, the mass is MA, the volume is 1. So the density is just equal to the mass. That's actually the definition of density. If an object has, or a substance has uniform density, then each meter cubed of the object has a mass equal to the density. Okay, the density is the mass per meter cubed, if it is a uniform density, as in the case of most liquids. Okay, we do the same for liquid B. 1 meter cubed of liquid B has mass MB, so the density of liquid B is just MB divided by 1, or MB. Now, let's get the density of the mixture. Let's suppose we mix these liquids together. We add 1 meter cubed of liquid A to 1 meter cubed of liquid B. That means we get 2 meters cubed of the mixture AB. What is its mass? Well, we just add the masses of the liquids, that's MA plus MB. But now you see that MA plus MB is just rho A plus rho B. So how do we get the density of the mixture? Well, we just get 1 meter cubed of AB, because the density is just the mass of 1 meter cubed. So all we have to do is divide this by 2. Rho A plus rho B divided by 2. Alright, so that's the density of the mixture. It's just the mean of the densities of the constituent liquids, actually. We add the densities and divide by 2. We might have guessed this, but it's still good to prove it, I think. Now, we could set this thing here equal to this thing here, because they're both equal to the same thing, namely W. But the problem with that is that we won't be able to cancel out the rho A. And we won't be able to get VAB in terms of V. That's what we're after. We want the volume of this region here, which I'm calling VAB, in terms of V, the volume of the cylinder. Okay, so we can't just equate these two. what we could do is write row A in terms of row B. Set these equal to each other. Get row A in terms of row B. That's easy because the V's and the G's will cancel. And then we can plug in here and get this thing in terms of row B only. When we've done that, then set this thing equal to this thing, and the row B's will cancel out. Okay, so let's do that. So we put this equal to this. See, we can get one density in terms of the other. Okay, we get 1/3 row A equals 3/5 row B. Multiply both sides by 3. Row A is 9/5 row B. Now let's go up here and replace row A with 9/5 row B. So we're going to have 9/5 row B plus row B divided by 2 times the volume of the immersed part of the cylinder in the mixture times G. Now, what we can now do is set this thing here equal to this thing here. Because if we do that, we can cancel row B on both sides. We can cancel the G, and then we're left with VAB in terms of V. Exactly what we want. So I'm equating this with this. So we divide both sides by row B. Divide this by row B. So on top we get 9/5 plus 1 divided by 2. Well, 1 is 5/5. 9/5 plus 5/5 is 14/5. Divided by 2 is 14/10, which is 7/5. So this thing here becomes 7/5 VAB. Well, the G's go on both sides as well. And we're left with 3/5 V from this thing here. So how do we get VAB? We just multiply both sides by 5/7. Well, we can cancel the 5's. Divide both sides by 7, so 3/7 V. So in the mixture, 3/7 of the axis of the cylinder is immersed, which means that 3/7 of the volume is immersed.